Hi, everybody. Thank you for coming. I'm sorry that I brought the wonderful Pittsburgh weather to sunny California. Today, I'm going to be talking about scaling video analytics on constrained edge nodes. This is joint work with a number of my colleagues, as well as my advisors, Dave Anderson and Michael Kaminsky. As you all know, in this day and age, cameras are proliferating in smart cities. Technological advancements and economies of scale have made camera deployments ubiquitous. The point of all this observation of the world is so that computers, not people, can reason about the world. Because of the research that people like all of us are doing, the number and diversity of applications processing this data is exploding, from things like traffic analytics to customer tracking and more. My talk today is about our investigation into how to handle this explosion of video data at the edge. In this talk, I'm going to first discuss some constraints and challenges that we have encountered in our practical experience with camera deployments. We've actually worked on one of these things around Carnegie Mellon. Then, I'm going to introduce a new edge-to-cloud system called Filter Forward that addresses these challenges by enabling application-specific video filtering on the edge. And finally, I'm going to discuss a new flavor of cheap but accurate neural network filter that we call microclassifiers, which are the building blocks of the Filter Forward system. In this work, we are considering a type of deployment architecture that consists of large numbers of streaming cameras, always on, connected to some kind of local compute edge node. This edge node has a low bandwidth connection back to the data center. Complex analytics applications, bulk analytics, are running in the data center on GPUs or custom hardware accelerators. The fundamental problem here is that as the number and resolution of these cameras increases, we're generating way too much data. We can't offload all the data to the cloud for processing, where our big compute is. So we need some way to save bandwidth. And let's start by looking at a couple of straw man ideas on simple ways that we could potentially do that. One technique you might consider is to look at some part of this really big frame, and try and figure out which region applications are interested in and only transmit that region. The problem with this cropping model is that if you're only sending a little part of the frame, then you're kind of defeating the purpose of having such a wide, expansive view of the world from so many cameras. Furthermore, applications are interested in all sorts of content here, like people walking by on the sidewalk, cars driving by, trucks entering and exiting the construction site. It's hard to decide which piece of the data you'd send. So generally speaking, we don't think we can crop this data. But what if we just really heavily compress things or reduce the spatial resolution? Compression encoders like H.264, H.265 are really good these days. However, because these viewpoints are so wide, important details that applications need are typically really small and hard to see. Compression and downsampling destroy these subtle details. These applications are relying on these details for their complex processing in the cloud. Consider, for example, a person walking by the street here. Even at relatively high quality, 7 megabits per second, it's hard to see, for example, what type of clothes they're wearing if you wanted to see something about the person. If we compress down to 100K, you can't see anything at all. So generally speaking, we don't think that compression alone is the answer. So what are we going to do with all this data we have at the edge? If we can't compress it, we can't crop it. In this work, we're going to target a particular type of application that are interested in rare events, like specific makes and models of cars, particular regions, etc. If we consider this type of application, then by definition, large periods of time don't contain data that we care about. What we can then do is take the well-known idea of early discard and push it to the edge. This gives us the opportunity to realize a big bandwidth savings by discarding data that doesn't matter. However, by pushing the filtering to the edge, we introduce another challenge. Whereas cropping and compression are relatively lightweight and easy to implement in hardware, complex application-specific filtering like we want to do is not trivial and requires many more CPU resources. So by focusing on these rare events, we've opened the door for saving bandwidth, but now all of a sudden we have to worry about compute. The work that I'm going to talk about today tries to address this. And I'm going to propose a system called Filter Forward, which saves bandwidth by filtering relevant data at the edge while supporting scalable multi-tenancy, multiple applications. Let's dive right into an overview of the Filter Forward architecture. We have an edge node, we have a data center, we have user applications, complex analytics running in the data center. Our filtering is going to be happening on the edge node. That's where the interesting stuff is. We have frames coming off of one or more cameras. And then this is the part where Filter Forward comes in. We're going to build off the concept of modern object detectors, and we're going to use a feature extraction deep neural network. In our case, we're using MobileNet to extract semantic features about each one of these frames. We're going to look at these deep neural network activations, treat them as feature maps, and then we're going to feed these feature maps, which contain all the semantic content about what's going on in each one of these frames, into a set of custom lightweight networks called microclassifiers. The key contribution to this design is that by using a feature extractor to generate the input to these microclassifiers, we're amortizing the expensive pixel processing, which takes up most of the compute, across all of the applications. Let's look a little bit more about these microclassifiers. They are fundamentally the building blocks of the Filter Forward system. They are small, individually trainable neural networks that determine if a single frame is relevant. Once we have these per frame decisions, we take them and we smooth them into contiguous event detection windows, which are then re-encoded and transmitted back to the data center. Our fundamental reason for choosing a design like this is by sharing the pixel processing between all of the microclassifiers and only operating on these high-level feature maps, we're able to make this system much more computationally scalable for large numbers of applications, large numbers of microclassifiers. Now, if you recall, another thing I brought up was that it's really important that we be sensitive to fine-grained details, because with these wide-angle videos, things are really small far away. The way that we've done that is twofold. Instead of really heavily downsampling our images before we process them, like is typical in object detectors and image classifiers, we operate on full resolution frames. This, of course, gives a big computation overhead. If you're processing a 1080p image instead of something that's 224 by 224, you're doing a lot more work. However, because the microclassifiers are lightweight, we're able to amortize that away effectively. The second part is that we give them the flexibility to pull from any intermediate layer in our feature extraction network. This is a key way that we can fine-tune the microclassifiers based on the granularity of the type of task that they're operating on. Another important thing to note here is that because the microclassifiers are completely independent of each other, they're not ingrained in the same network, they are individually trainable. This is important because in real-world deployments, applications come and go all the time. If we had used a monolithic multitask network or just fine-tuned an object detector, for instance, we would then need to retrain the whole network whenever an application arrived. And from a deployment practicality point of view, that doesn't really work for us. In our paper, we propose 3 different microclassifier architectures. I'm going to talk briefly about them here. The first is just a simple 3-layer convnet, uses 1-by-1 convolutions to expose fine details in the feature maps. Unlike normal transfer learning, which keeps the fine-tuned portion of the network constant, by making custom microclassifier networks like this, we're able to specialize the types of applications that are operating on this wide-angle surveillance video. Remember that we're processing full resolution frames, so these networks are a little bit more expensive than you'd think if you were just operating on really small 224 by 224 images. We also have a couple of other architectures that we designed. A localized binary classifier that is designed to pick out prominent objects in a localized view. So if you, for instance, if your application knows that it's interested only in content in a particular region. An important thing to note here is that we're not actually cropping the original pixels, we're cropping the feature maps. So we're still sharing the same base deep neural network with the rest of the microclassifiers to retain our scalability. And then we have a temporally windowed version of the same localized binary classifier that gives us a little bit better accuracy because we're looking at a window of frames. An important detail to remember here is that applications are allowed to mix and match these different architectures based on their requirements, what they're trying to detect. A diverse set of these applications will be running at the same time on an edge node, all sharing the feature extraction deep neural network, all extracting from different layers, different intermediate activations. And please see our paper for more details about these. I want to now give you a bit of a preview of our evaluation. Of course, more details are in the paper. We looked at a couple of real-world data sets that allowed us to demonstrate the capabilities of our microclassifiers. In the first data set, we were looking for people in this crosswalk region. So the localized classifier is helpful because we were allowed to discard parts of the frame that weren't necessary and tell the classifier that we were interested in a particular region. For the second data set, which we actually collected from our deployment near CMU, we're trying to find people with specific details in their clothing, like if they have a red shirt on or a red hat. And this was really, really hard because those details are tiny and they get destroyed really easily by compression. The pixels really, really matter a lot. In this case, the full frame object detector, the first one that I described, is really well suited to exposing these details. And the figures that I present now are going to primarily deal with the second data set. When evaluating filter forward, let's think back to the original challenge that we were trying to solve. We want to save bandwidth by dropping irrelevant frames. So first, we're going to evaluate how our event detection accuracy changes as we reduce our bandwidth usage compared to the more practical of our baselines, full stream compression. Then, because we're pushing this filtering to the edge where resources are constrained, we need to investigate filter forward's throughput scalability as we add more applications. For this, we're going to compare it to another method of designing lightweight classifiers. We looked at the NoScope paper from 2017, which proposes a cascade of various filters that protect access to an expensive base deep neural network, or expensive deep neural network. This is designed primarily for bulk analytics, but it's also applicable to edge filtering. They design lightweight binary classifiers that operate on raw pixels, and we call these lightweight classifiers discrete classifiers. The important difference to remember between these discrete classifiers and filter forward's microclassifiers that I just talked about is that the discrete classifiers are operating on raw pixels, so each one needs to do a full translation from the original input to some decision about whether a frame is important. By operating on the features extracted from a base deep neural network, our microclassifiers are much more computationally scalable. Let's first take a look at our bandwidth savings. What we're going to show is the event detection accuracy as we vary the bandwidth use. As an accuracy metric, we're using a notion of event F1 score that's based on a paper from last year's SysML. See our paper for more details about how we adapted that metric. Here are the results if we compress the entire stream and run the processing in the cloud. As we increase our bandwidth that we allow the system to use, the accuracy increases as well, as you would expect. What filter forward allows us to do is take basically any point on this curve and switch it to the left by dropping unnecessary frames. In this particular case, we preserve our accuracy while using 6x less bandwidth. The 6x, however, depends a lot on the specific task. Of course, if your target event is present in all frames, then filter forward is not going to be able to save you the bandwidth there. The real takeaway here is that if there is bandwidth left on the table by data that you don't care about, Filter Forward will find that, and it will concentrate your bandwidth use on the data that matters, the frames that matter most. Now, before we talk about end-to-end performance, let's look specifically at the cost of each microclassifier. Here we're analyzing how computation cost in terms of multiply adds, number of multiply adds, impacts event detection accuracy. We're comparing to the pixel level discrete classifiers that I described earlier, using the same event F1 score metric as the previous graph. Microclassifiers achieve slightly higher accuracy, but have a much, much lower marginal cost. This is because they're operating on the features instead of raw pixels. They're able to be much less complex. They're just taking a semantic representation to a final decision, not pixels to a final decision. What this slightly higher accuracy shows is the benefit of being able to use a really powerful base network for our feature extraction. Using a network like MobileNet that has a lot of sensitivity would normally be just too expensive to do on every frame. But in Filter Forward, because we're amortizing that cost across all of our classifiers, we're able to realize that benefit. Finally, let's take a look at end-to-end performance scalability. We're looking at how the rate at which we process frames changes as we vary the number of classifiers. In addition to comparing to discrete classifiers, as before, we're also looking at a more simple baseline of just running multiple copies of a fine-tuned MobileNet, one for each application. We ran these experiments on a 4-core Intel CPU, similar to what we've actually deployed. And so the numbers on the y-axis don't really matter. It's more the trends that matter. As you would expect, running a full MobileNet for each application causes the performance to drop off pretty fast. Didn't really think that that was going to work out. The discrete classifiers, on the other hand, being much less complicated than a full MobileNet, achieve a much higher throughput up front, but because they're duplicating a lot of pixel processing, their throughput also drops off pretty quickly. Filter Forward, on the other hand, incurs an upfront overhead and is slower for lower numbers of applications than the discrete classifiers because of this base deep neural network. But by the time we're running 4 classifiers, Filter Forward achieves the highest throughput of these systems. And by the time we get to 20 classifiers, Filter Forward is 4 times faster. Again, the reason for this is because each microclassifier is so lightweight that adding more and more really doesn't change your throughput all that much. The vast majority of the computation is in this shared base deep neural network. Ultimately, if you have more than a couple of applications, Filter Forward is going to give you a big throughput win. All right, I'm basically out of time, so I'd like to summarize. Filter Forward is a new system for video analytics on the edge. We're able to save a lot of bandwidth and get much higher throughput with modest numbers of classifiers. At the core of our design is a new architecture for application-specific neural network filters called microclassifiers that have a much lower marginal cost than existing work. If you're interested in learning more, please come visit me at the poster session or check out this URL. Thank you very much.
All right, so this paper's open for questions.
Yes, so one clarification is that here you will determine, let's say that I have n frames, and then you will determine which frame is useful to send to the data center, right?
That's
so
correct.
Conceptually, what you're doing is kind of like attention-based selection. So I'm curious why we need to have a different kind of a micro classifier when attention-based model will do the exactly same thing, right? I mean, in the CV community, people are using attention-based model to select like a useful train, for example, to generate the captions. So can you contrast your approach against, let's say, the attention-based approach, and then why yours is better?
I think I agree that there's a lot of other ways you could solve this problem in the CV community. Attention-based mechanisms are one of them. However, we approach this from the system architecture design point of view. I'm fundamentally a systems researcher, and so I looked at how can we share computation, how can we avoid doing redundant work? And that's really why we arrived at this design, but I completely agree that there are plenty of other interesting ways that we could solve this problem in the CV literature.
Thanks, Akansha from Google.
I had a question on how I would go about training these microclassifiers because I would need the queries up front in some ways for me to know what I'm training for. And today, a lot of the mobile nets are trained general purpose.
Yes, excellent question. The microclassifiers themselves are trained independently by whichever entity is developing a particular application. So if I was trying to develop an application that let me know if people were wearing blue jackets, I would query the video deployment for a set of representative data from these cameras. I would go about labeling it, and then I would train the microclassifier myself. And what I give to Filter Forward as an application developer is the architecture of the microclassifier, frozen weights, and then a specification of which intermediate layer from the base deep neural network I want to operate on, and if I want to optionally crop that intermediate layer. So the training is handled not by the system as a whole, but as each individual user, so that they can keep the data separate.
It seems like a chicken and egg problem, right?
Yeah, it does. And it's still a developing field that we're trying to figure out all the questions just like that. Thank you very much.
Do you have any sense of how the accuracy of the mobile nets that you use compared to, say, more accurate methods such as like MassCar CNN with like a 152-layer ResNext or something?
That's a really interesting, excellent question. In this work, we didn't particularly look at how we choose this base deep neural network. We picked MobileNet because it was pretty accurate and lightweight, and we were running on like CPUs on edge nodes. I think it's a really interesting direction for future work to try different architectures. And one thing that pushing more compute resources to the edge and giving yourself more of a budget would allow you to do is play with more expensive techniques that give you better features than, say, something like MobileNet would, which is a few years old now. Thank you very much.
All right, let's thank our speaker.